There's a palpable buzz in the air right now around the newest wave of advanced AI models. I mean, these aren't just smarter predictive text generators anymore.
No, not at all. They seem to be doing something, well, something more, like thinking internally.
Exactly. They tackle problems by generating intermediate steps, before giving an answer. We're hearing terms like thinking models or reasoning models thrown around everywhere.
And it's really fueling this idea, isn't it, that maybe we're seeing genuinely significant steps towards artificial general intelligence, AI that can reason broadly, more like a human.
Yeah, that sense of excitement is definitely understandable. When you see these models generating what looks like a step-by-step breakdown to solve some complex query, it certainly feels like a leap forward.
It really does. It suggests they might be getting a deeper understanding, not just, matching patterns they've seen before.
But here's the big question. How real is that thinking? Is it truly generalized reasoning, the kind that scales up, or is it maybe a very sophisticated illusion?
That's the crucial question, absolutely, and it's exactly what we're planning to plunge into today.
Right. We're doing a deep dive into a recent research paper that takes a really meticulously designed approach to poke and prod these advanced AI reasoning models.
It looks specifically at their capabilities and, maybe more importantly, their fundamental limitations.
The source material for this is a paper called roughly The Illusion of Thinking, Understanding the Strengths and Limitations of Reasoning Models via the Lens of Problem Complexity.
And it's fascinating work. It comes from researchers, and some are associated with major tech players like Apple. They've come up with a pretty unique way to test these models that goes beyond the standard benchmarks we usually see.
So our mission today is to unpack the core findings of this paper for you. We'll explore what their experiments reveal about how these models actually perform as tasks get harder.
And what the model's own generated thoughts actually look like under the microscope.
Yeah, and whether they truly stack up to some of the, let's say, ambitious claims about approaching general AI. Consider this your shortcut to grasping the essence of this really cutting-edge research.
Okay, let's set the stage then. What exactly does this paper mean by large reasoning models, or LRMs?
Good question. So building on that initial idea, LRMs are kind of a newer evolution of the large language models, the LLMs we hear so much about.
Right.
They've been specifically architected or trained with an emphasis on solving tasks that seem to need explicit reasoning steps.
Okay.
We've seen examples pop up like OpenAI's O1 and O3, DeepSeek R1, Claude 3.7, Sonnet Thinking, Gemini Thinking, those kinds of names.
Got it. And the defining characteristic the paper points to is their ability to generate these detailed intermediate processes, these thinking traces, before they get to a final output.
Exactly. This often involves techniques like chain of thought, where the model basically narrates its step-by-step approach, or other kinds of internal self-reflection.
And for listeners maybe less familiar, chain of thought is essentially the model showing its work, right? Making its process visible.
That's a good way to put it. And this capability, combined with some pretty impressive results on various standard tests, well, that's why you hear many experts suggesting these models are indeed taking significant strides towards more general AI.
Because articulating a thought process feels qualitatively different. It's not just predicting the next word based on patterns anymore. Or at least it seems that way.
Right, that's the context. However, the paper introduces a really critical perspective here. It starts asking, okay, do these promising benchmark results truly indicate generalizable reasoning? Reasoning that holds up under pressure.
How do these models perform when problems get significantly more complex? Are there inherent limits to this thinking process they seem to be doing?
And this leads them to critique the common evaluation methods. Those standard benchmarks, like for math or coding challenges, they measure performance, sure.
But the paper argues they have real limitations. For one, there's the possibility of data contamination. The models might have just seen very similar problems during their training.
That's a huge point. And maybe more importantly, these benchmarks often just check the final answer. They give you almost no insight into how the model actually got there.
Right. Did it genuinely reason it out? Or did it recognize a familiar pattern? Or maybe even partially memorize a solution structure it saw in the training data? Standard benchmarks often can't tell you that difference.
So how do you create a testing environment where you can be more confident you're probing genuine reasoning and not just, say, sophisticated retrieval or pattern matching?
That's the challenge the researchers tackled head on. Instead of relying only on those standard tests, which can be a bit opaque,
They designed what we can think of as a puzzle lab. They used controllable, rule-based puzzle environments.
And this is really a key innovation in the paper. They picked classic, well-defined problems, things like the Tower of Hanoi.
Moving the discs between pegs.
Right, or checker jumping, river crossing.
It's the wolf, goat, and cabbage type thing.
Exactly, those constraint problems. And also, blocks world stacking colored blocks in specific sequences. Most people have probably encountered some version of these.
And these weren't chosen just because they're, fun little brain teasers. The source material highlights several really critical advantages to using these puzzles.
Okay, like what?
First, they offer precise control over complexity. You can just add another disc to the Tower of Hanoi or another person to the river crossing problem.
And the difficulty scales up predictably.
Yeah.
Often exponentially. You know exactly how much harder you're making it.
Second, using specific, maybe slightly obscure instances of these puzzles helps minimize that data contamination risk we talked about.
Right. It's less likely a model memorized the exact path for a weird river crossing setup compared to, say, a common coding problem found online.
Third, these puzzles strictly require algorithmic reasoning based only on the explicit rules given in the prompt. There's no ambiguity, you have to follow the logic.
It's a pure test of deduction within a defined system. No outside knowledge needed, just the rules.
And maybe the most important point, this setup allows for really rigorous evaluation using sophisticated simulators.
Ah, okay. So the simulators can check the work.
Not just the final answer. They can validate every single step the model proposes in its intermediate thinking traces. They check if each move is valid according to the puzzle rules.
Wow, okay. So they don't just see if the blocks are stacked right at the end, they check if every single block move the model said it would make was legal.
Exactly. That simulator capability is a game changer. It gives this unprecedented window into how the model is trying to solve the problem.
It lets the researchers examine the internal thoughts themselves, not just the final output. Moving beyond the illusion, like the title says, and looking at the mechanism.
Right. So what happened when they put these LRMs, the thinking models and standard LMs, through the paces in this puzzle lab? They cranked up the complexity higher and higher.
And this is where the results get particularly revealing about the current state of AI reasoning. The paper identifies what they call 3 regimes of performance, depending on the problem's complexity.
Okay, lay them out for us.
All right. In the first regime, at low complexity, the finding was actually pretty surprising.
How so?
The standard non-thinking LLMs, the ones just generating an answer directly, they performed comparably, sometimes even better than the LRMs.
Really?
Better, yeah. And not only that, they were more token efficient. They used fewer computational resources to get the answer. For these simple problems, it seems the extra thinking steps the LRMs generated were unnecessary, maybe even slightly detrimental.
Huh. That feels really counterintuitive. You'd think a model designed for reasoning would ace the easy stuff.
It suggests maybe for easy problems, direct pattern association or just a single pass generation is actually more effective than spinning up this whole elaborate multi-step process.
Okay.
But then things changed in the second regime, at medium complexity. Here, the LRMs finally showed their expected advantage.
Ah, okay. This is their sweet spot.
Exactly. This is where that additional effort of generating detailed reasoning steps actually paid off. They could solve problems that the non-thinking models started to struggle with.
Right. So the thinking mechanism does provide a benefit, but apparently only when things get moderately difficult. So what happens when the problems get truly hard?
Well, that brings us to the third regime, high complexity. And here, the paper reveals a pretty stark reality.
Uh-oh.
Both model types, the thinking LRMs and the non-thinking standard LLMs, experienced a complete performance collapse. Beyond a certain complexity threshold, accuracy across the board just dropped, essentially to 0.
Wow.
Even the LRMs, despite generating pages and pages of what looked like reasoning, simply could not find a solution.
A complete collapse. They just hit a wall. That's a significant finding, especially when you think about claims regarding progress towards generalized intelligence. That implies robustness, right? Handling increasing difficulty.
Precisely. And the paper observes something else really intriguing near this collapse point, something they called a scaling limit.
Scaling limit, what does that mean?
Yes, this is a particularly insightful detail. As the problems got harder and edged towards that collapse threshold,
Yeah.
the LRMs started reducing the amount of reasoning they attempted. They actually generated fewer thinking tokens.
Wait, hang on. They generated less thinking when the problem got harder.
Exactly. Even though they had the capacity, the budget, to generate more tokens, they generated fewer.
That seems completely backward. True reasoning, you'd think, would involve more effort, deeper thought when faced with a tough challenge.
Precisely. It's a critical observation. It implies the models aren't just failing because they need, say, more time or compute to think it through.
So it's not just running out of steam.
It seems not entirely. It suggests they encounter some kind of inherent limitation that actually causes them to constrain their own exploration process when the problem exceeds a certain, maybe surprisingly low level of complexity or required steps.
So not only do they collapse on hard problems, but they also seem to have this weird self-imposed or maybe inherent limit on how much they'll even try to think it through.
That's what the data suggests. It points to a potential fundamental barrier in scaling their reasoning process itself.
Okay, but what about the content inside those thinking traces, especially for the problems they could sort of tackle in that medium range? You said the simulators let them look at the steps themselves.
Right, and this is where the analysis gets really granular. By checking the validity of each proposed move in those traces against the puzzle rules, they saw different patterns emerging depending on the complexity level.
Okay, tell us about those patterns. What did the thoughts look like?
Well, for the simple problems, remember, where the standard LLMs sometimes did better.
Yeah.
The LRMs would often find the correct solution path relatively early in their generated thoughts, like pretty quickly. But then kind of inefficiently, they'd just keep going, generating more thinking tokens, exploring incorrect solutions, or wandering down dead ends.
Huh. The paper called this the overthinking phenomenon, right?
Exactly. They solved it quickly internally, but then kept generating noise in the output.
So they found the answer, but then couldn't stop thinking, or maybe couldn't recognize they'd found it confidently. Sounds like a lack of efficient termination or self-assessment.
It definitely indicates an inefficiency in processing, or perhaps validating their own findings. Now, at moderate complexity, where the LRMs had their advantage.
The sweet spot again.
Right. The pattern was different. Here, the models tended to explore incorrect solutions first. They'd make multiple wrong turns in their thinking traces before eventually arriving at the correct solution path, often much later in the generated sequence.
Okay, that feels a bit more intuitive for harder problems, maybe. You'd explore some dead ends before finding the right way. Trial and error.
Yes, it shows some ability to explore and potentially maybe self-correct. However, in the high complexity regime where everything collapsed,
Where they got zero accuracy.
in that regime, the thinking traces were basically useless. They contained no correct solutions at all, not even valid steps towards a solution. The model wasn't just finding the solution late. It couldn't even generate a single correct move towards it within its allocated thinking budget.
Wow. So looking inside the thoughts just mirrors the external collapse. It shows inefficiencies, some misguided exploration, and then just a complete lack of capability beyond a certain point.
Exactly. It suggests these limitations are pretty fundamental to their internal reasoning process, not just some fluke in producing the final answer.
Okay, so beyond these complexity regimes and the trace analysis, the paper also uncovered some genuinely counterintuitive behaviors, things that really make you pause and question the nature of their current capabilities.
Yes, there were a couple of really striking findings. One was related to what they called the failure to execute algorithm.
Failure to execute.
Yeah. So in the Tower of Hanoi puzzle, which needs that very precise sequence of moves, the researchers didn't just ask the model to solve it from scratch.
What did they do?
They actually provided the explicit, correct algorithm for solving the Tower of Hanoi right there in the prompt itself.
Whoa, so the model didn't have to figure out the plan, it just had to follow step-by-step instructions. That should make it dramatically easier, right?
You would absolutely think so. Executing a known recipe is usually much simpler than inventing the recipe.
Yeah.
But the paper found that providing the algorithm did not significantly improve the model's performance. The collapse point, where accuracy went to zero, still happened at roughly the same complexity level, the same number of disks, as when the models had to figure out the algorithm themselves.
No improvement, even with the answer key, essentially.
Very little, if any. This strongly suggests their limitations aren't just about high-level strategic planning or finding the solution path. They seem to struggle with consistent logical verification and just reliable step-by-step execution, even when the steps are handed to them on a silver platter.
It's like having the perfect map and instructions, but still getting lost turning out of the driveway if the journey is slightly long.
That's a good analogy. It points to a potential brittleness in just following logical rules consistently over a sequence of steps.
That's a really surprising limitation for systems we hope might one day execute complex multi-step tasks reliably. What else did they find that was puzzling?
Well, there was also this notable inconsistent reasoning across puzzles. This was quite interesting.
Inconsistent how?
Okay, so take the same model they mentioned, Claude 3.7 Sonnet thinking specifically here. In the Tower of Hanoi puzzle, it could sometimes make sequences of remarkably error-free moves quite deep into the puzzle.
Like how deep?
They noted instances of correctly executing maybe 100 moves for a moderately complex N10 problem.
100 correct moves in a row. For Tower of Hanoi, that actually sounds pretty impressive, given how many possibilities there are.
It does, right, for Tower of Hanoi. But then, the very same model would fail extremely early in the river crossing puzzle.
The wolf and goat one.
Yeah. Sometimes making its first incorrect move and completely collapsing within the first 5 steps for a simple N3 problem instance.
Okay, hold on. An N10 Tower of Hanoi puzzle. The shortest solution is over 1,000 moves, 2023 to be exact. Making 100 error-free moves there is significant progress.
Right.
But an N3 river crossing puzzle only requires, 11 moves optimally? Failing within the first 5 steps on a puzzle needing only 11 total steps is, well, that's much worse performance in relative terms, isn't it?
Exactly. It's a stark inconsistency. Making 100 correct steps on a 1,000-plus step problem versus failing before step 5 on an 11-step problem.
So performance doesn't seem purely tied to the inherent logical complexity or just the raw number of steps needed in some abstract sense.
That's what it looks like.
Yeah.
And the paper suggests this might hint at the continued, perhaps heavy influence of the training data. Maybe Tower of Hanoi sequences or similar kinds of state space searches are just more common or better represented in the vast data sets these models train on.
Compared to specific river crossing scenarios, especially maybe for n greater than 2, which might be rarer online. Potentially, yes. So the model seems capable and logical in one domain because it resembles things it's seen, but becomes brittle and fails quickly in another slightly different structure domain.
So what looks like generalizable reasoning might still be quite tethered to whether the model has encountered very similar problem structures or solution patterns during its training phase.
That's a strong implication from this inconsistency finding, yeah.
Okay, let's try to pull back then and summarize what this deep dive into the paper really tells us about the current landscape of AI reasoning models, especially considering all the hype and expert claims out there.
Yeah, I think the core takeaway is that this study, using its really careful methodology with these controllable puzzles and step-by-step evaluation, it provides pretty strong evidence of fundamental limitations in the current generation of large reasoning models. Despite their ability to generate these thinking traces and all the enthusiasm for their potential,
they don't seem to exhibit true generalizable reasoning capabilities that scale reliably as problems get harder. Exactly. We saw that clear pattern. Standard models doing okay or better at low complexity, the LRMs showing an advantage only in that medium range.
And then both hitting a hard wall, a collapse at high complexity.
And critically, we saw that counterintuitive scaling limit, where the LRMs actually reduce their reasoning effort just when things get tough, suggesting a barrier in the reasoning process itself, not just needing more compute.
Right. And looking inside the thoughts wasn't much better. It revealed inefficiencies like that overthinking on simple problems, and then a complete inability to even generate correct steps on complex ones.
And finally, those really surprising findings, the struggle to simply execute an algorithm they were given, and that significant performance inconsistency across different types of puzzles.
Yeah, those really point towards limitations that might be rooted more in the model's architecture or their dependence on training data patterns, rather than reflecting pure, scalable, general reasoning ability.
So the bottom line seems to be that while models like, OpenAI's O1, Claude 3.7 thinking, Gemini thinking, they're undoubtedly advanced, they perform well on specific tasks and benchmarks that maybe play to their strengths or training.
But these findings strongly challenge the narrative, or at least temper the enthusiasm, that current LRMs represent an unimpeded path or even a major leap towards genuine, robust, generalizable AI reasoning.
It really suggests we might be encountering some fundamental barriers with the current approaches, especially when complexity increases or the problem structure deviates even slightly from what the model might have implicitly learned from its training data.
Which leads us to a pretty crucial set of questions, doesn't it?
I think so. Given these findings that even the AI models explicitly designed to think seem to collapse when complexity ramps up, struggle with basic reliable execution, and show surprising inconsistency.
What does this realistically mean for the kinds of truly complex, novel, perhaps safety-critical real-world problems we might be considering delegating to AI in the near future?
And maybe just as importantly, how can researchers and engineers actually build systems and then rigorously test them for something as profound as generalizable reasoning?
Yeah, how do we ensure it's not just a sophisticated illusion of thinking, as the paper puts it? An illusion that looks good on benchmarks but breaks down under real pressure or novelty.
How do we build and verify a robust, scalable capability that we can actually rely on? Those are the critical questions this kind of research forces us all to confront as this technology continues its rapid evolution.
Absolutely. Well, thank you for joining us for this deep dive into the fascinating and perhaps slightly cautionary findings about the current state of AI reasoning models.
Hopefully gives you some food for thought.
Definitely. Keep these insights in mind as you watch the progress and, importantly, the claims being made in the world of AI.